So at the end of your data collection for Tracker, you have a set of data that corresponds to time and where your object was in both X and Y. We need to take this now, graph it, and then try to manipulate the graph to see if we can find out about both the position-time relationships and the velocity-time relationships. Here's what I mean by that. So we've seen that when we graph this data, we get a parabola. And we've developed in class what the equation for that parabola might be. What we didn't justify so far in class was that the velocity time graph looks like this, linear. So I think what we need to do now is make a velocity time graph from the position time data that you guys have. And the way to do that is to take the slope at different places along your parabola. So we're going to grab a couple data points that are close to each other, and we're going to get the slope between them. Here, early on, then later, then later. We're going to graph those and see if we indeed do get a linear velocity time graph. Now that sounds like a lot of work, so we're going to have a spreadsheet do it for us. So I like to use Google Drive and Google Sheets as my spreadsheet program. This can work in Microsoft Excel. It can work in LibreOffice. It really depends on your preferences. The graphing part will be different, but the calculation parts will be the same. So go ahead and, if you're using Google Drive, upload your CSV file from Tracker into your Google Drive somewhere and open it. It should give you the option to open with Google Sheets. So this opens a spreadsheet program. Spreadsheets are what a lot of people use to manipulate numbers. They're not just good for science. They're good for finance. They're good for running a small business. If you have to do any sort of repetitive calculation, like take the slope constantly along a graph, it'll be easy. But it's also good if you have to calculate people's payroll or things like that. So the first thing we need to do to kind of customize this lab for ourselves is we're not going to look today at the horizontal X data. We're going to look at the vertical Y data. So what we'll do is we'll actually delete this whole column. So I'm going to right click, delete column. That's the data we need. Notice it's in scientific notation because that's how Tracker records things. Don't worry about that at all. Alright, so let's get a position time graph made in Google Sheets first, just so we can see what we're looking at again. Graphing's pretty easy in most spreadsheets. In Google Sheets as of 2020, here's how I like to do it. I first highlight a cell that's nowhere near my data, because most spreadsheets, when they try to guess what you want them to graph, mess it up. By clicking on the Insert Chart button, you get a nice blank graph that's all yours to customize. And for some reason, Google Sheets works better if you click on Add Series or Add a Y-axis first. So all you do is highlight all your data and click OK. And then you say you want to add an X-axis. You got to click this little thing here or else it messes up your graph. And you just do the same thing with your X-axis values, which for us is time. Alright, so now what we've got is a bar graph, which is not useful for us, although it is kind of pretty. We want to have an XY scatter plot. So we just go find that. Alright, there's our beautiful parabola. So we need to do a couple things to make this chart usable. First of all, we need to put some titles on there. So let's on the horizontal axis, or the x-axis, let's say this is time in seconds. And on the vertical axis, let's say this is position in meters. Okay, that's looking pretty good. We also should probably get the best fit line for this. And to do that, you go to Series, and trend line is somewhere here. And every time you click on an option, it gives you more options. Obviously, it's not a line. We know it's a parabola, which is a polynomial of order 2. And then if you want the equation, you click Label, Use Equation. All right, so that's our position time graph. So what I would like to do is get a velocity time graph. And I'm going to do that by getting the slope between every 2 consecutive data points. Now that sounds like a lot of work. And this is why a spreadsheet can really be our friend. A spreadsheet is set up to do repetitive calculations over and over and over again so that you don't have to. So let's remind ourselves what the slope formula is. We know that the slope on a position time graph gives us the velocity. So we need to do 2 distance points subtracted from each other divided by 2 time points. And we're going to do that between every consecutive pair of points. So instead of entering something that looks like this, an algebraic formula in a spreadsheet, we're going to enter something that looks like this. And the things that are here are actually the coordinates. Like, for example, B5 is B5, this number right here, of our data points. And what this is doing is telling the computer where to look for data and then what to do with that data. So what that can get you is something like this. Let's make a new column that says velocity. We'll label that with meters per second. Now I want to do like y2 minus y1. So I can't start with the first cell here. I have to start with the second one. So I have 2 y values to work with. To wake up the computer and say, hey, I want you to calculate something, you press the equal key. And then to do the top of the fraction, we should put a parentheses around it so it doesn't mess up order of operations. But here we go. y2 minus y1 divided by t2 minus t1. Boom. That's the slope between the first 2 data points. So the slope right here. Now I want to get all of these other slopes everywhere along this graph. And the computer can do that super easy. We just tell the spreadsheet to carry the formula down. So you highlight the cell you put the formula in, and there it is up there. You hover over this little blue square, and you click it and drag it. Boom. It's done all your other calculations for you. So what we want to do now is we want to graph all these velocities, all these slopes, versus time. We know that this graph is the x equals 1/2 at squared plus VOT plus XO equation. If we make our velocity versus time graph, we'll see if that's the V equals AT plus VO equation. Of course, that would be a line, so we should see if velocity versus time really is a linear graph. So we'll do that exactly the same way. We'll just click some random cell, insert chart, and in this case, we will add our series, which now is the velocities. And I need to apologize in advance if I yell during this. My cat is attacking my legs because she's awesome. Now we'll add in our x-axis. I'm going to leave that top one out because we didn't have one for velocity. Same deal. Cat, go away, please. Change this to a scatter plot. Why are you being not very nice? There we go. It is a line. All right. Well, that makes me feel good. We didn't break physics. So let's customize this graph. So we now have time on the horizontal axis. And we have velocity on the vertical axis. And this looks like a pretty decent linear graph, so we'll just add a linear trend line. And I think we're done. So we'll just try to show both of these at the same time. We can see that taking the slopes between every 2 points on a parabolic position time graph get us a linear velocity time graph. So this really could have the equation y equals mx plus b, v equals at plus vo. And we can see here that my a in this case is about 9. All right, I want to play one more time. Just like we took all of the slopes on the position time graph to get us the velocity time graph, we could take the slopes between points on this graph. In other words, what's the slope here versus what's the slope here versus what's the slope here, what's the slope here. And that should create for us an acceleration time graph. Now, you're probably looking at me like I'm a little crazy because this slope is constant. So there's only one slope the whole way out. So what should the acceleration time graph look like? Well, it should be something, since these slopes are all the same, it should be a horizontal line. And that is indeed what we get if we take the slope of our velocity time graph. So at the end of the day, all constant acceleration motion, you can describe it with a position time graph, which is a parabola. That gives us this equation. You could describe it as a velocity time graph. The slopes of at every point along this graph, if you plot them, you get a linear velocity time graph, which you can describe with this equation. And then, since this is a constant slope, the equation for the acceleration graph is super easy. It's just acceleration equals a number. Acceleration equals 5. Acceleration equals 10. So, out of our Angry Bird lab, where we literally spent less than a second doing this, we came up with some beautiful graphs that are going to help us explain essentially a whole class of how forces make objects behave. Gravity is a force that, at least in this room, doesn't vary as time passes on that bird. In other words, our acceleration graph is constant. Any force that's like that is going to have patterns of motion like this. We'll have a constant acceleration graph, it'll have a linear velocity graph, either increasing or decreasing, and it will have a parabolic position graph. So these can be used as models for how any object undergoing a constant acceleration, and therefore a constant force, acts. So on the album, you'll see these equations. You can look at them in detail, but this is their generic form. We have a position equation that relates time to position. We have a velocity equation that relates time to velocity. And those can be used for any force that acts like this. A few other big ideas that came out of this lab. We have this slope that's increasing, and then it's 0, and it's decreasing. The fact that we have equal slope but in opposite directions on either side of this peak, that tells us that here it's going up, there it's going down. And at the top with no slope, we have no velocity. Our velocity graph shows this too. We have an upward velocity, it decreases to 0 at the maximum height, and then it goes below 0 as it comes back down. There's a symmetry to this graph which is really interesting. If you look at the same point an equal amount of time before and after the peak, it's the same distance away from 0. This is symmetrical, which is why when you throw something, if you catch it at the height you launched it from, it's going the same speed on the way back down. That's why you should never, ever, ever shoot a firearm up in the air. The bullet will come back down at the same speed. So we'll use the equations that came out of this motion a lot to solve problems now. I just want to make a final point. They came from real motion. We didn't derive these using some mathematical formula. No one told you them. We measured something real. We made a model out of that real thing. Now we're going to use it and the equations it generated to understand other motions that are a lot like it. One final thing worth mentioning, the value of this line here, it's about -10. That's the acceleration due to gravity on Earth. So if it's falling or flying through the air, the acceleration is going to be 9.8 in the downward direction. That's the result of many experiments like this. If it's some other constant force, it may have a different acceleration, and we would plug that acceleration in instead.